Hello, welcome to the next video, the properties of ionic compounds. Okay, so we've looked at the structure and we know that ionic network lattices are rigid structures. We've got this guy here, there we go, pretty rigid. Okay, all the positive ions and negative ions are arranged in a regular arrangement, so they're rigid. So that's why crystals are hard. They do not conduct electricity in the solid state. So if you have an ionic solid, it does not conduct electricity, but become what are called electrolytes. They conduct electricity when they're in solution, aqueous, or molten. So if you melt them, they conduct electricity. They are brittle. Ionic compounds are brittle. Are soluble in water, often. Not all ionic compounds are soluble in water, but are often soluble in water. Usually crystalline solids have high melting points and boiling points. And I think there's one more. No! So let's go back. So what we're saying here is these are the properties of ionic compounds. And so our ionic bonding model has to explain these properties. And this is the important connection that you must make between the properties and the bonding model. So, what are the explanations? Well, they're rigid structures because the cations are strongly bonded to the anions. That's that electrostatic attraction. It's a very strong force, so it holds everything very rigid. They do not conduct electricity in the solid state because the rigid structures are not broken down and there's no free movement of ions. To conduct electricity, you've got to have ions or charges to move. Now normally in electricity, just what you plug into your power point, those charges that are moving, which are electricity, are electrons. However, they don't have to be electrons, and so we can conduct electricity with ions. But ionic substances do not conduct electricity in a solid state. They do in the aqueous and molten state because their structures are broken down and the ions are free to move. And we're going to expand on each of these shortly. Are brittle because pressure causes charges to align. Therefore they like charges repel and it shatters the structure. We're going to expand on each of these shortly. Are often soluble in water because the water molecules can disrupt the lattice and allow free ions to move. Often or usually crystalline solids because they have that three-dimensional lattice structure, and have high melting points and boiling points because there's that strong force again in the lattice holding it all together, so it takes a lot of energy to force them apart. So crystalline solids, there we are. Now, ionic solids are closely packed three-dimensional structures. Sodium chloride is an example, and you have an arrangement of sodium ions and chloride ions in a regular lattice. They have high melting points and boiling points because the strong bonding is throughout the lattice. A lot of energy is needed to separate the ions. Are non-conductors of electricity when solid because the ions are firmly bound in the lattice and there's no free charges to move. Will conduct electricity only if there's ions available. And we contrast that when we look at metals. Are hard because the ions are strongly bound. Again, that electrostatic force is strong. And the ionic bonds requires a lot of energy to break them. Often dissolve in water. Now the water molecules can move between the ions, positive and negative ions in the lattice, and free them up, and we'll show a little animation to show you that. When they dissolve in water, they dissociate and break apart to form ions that are free to move. Let's see if I can get this one working. Might take a little while, and I might have to cut a little bit out of this recording, but we'll see. Waiting. Oh, we're waiting. Maybe I shouldn't have done this. Maybe I should have had it already up. Ah, oh, we're back. Oh no. Oh, okay. Here's our little animation. Hopefully you can see that. So this is the sodium chloride. These are water, and the water molecules go in and steal. Each steals or an anion. You can see that the water molecules have captured one of these. And if we have a close-up view, this is the stealing of a chloride ion. So it gets surrounded by water. Okay, the water is actually attracted to that ion. Let's go back and the sodium ion is similarly stolen by the water, but a slightly different arrangement. Okay, and so let's play that again. The water molecules eat away at, let's play that again, eat away at the lattice, and it dissolves. So these ions are now free to move in the water solution and conduct electricity. Let's go back to this. Alright, so conductors electricity when molten or in aqueous solution. So that was an example of aqueous solution. It's because the ions can slide past one another and are therefore able to conduct electricity. That's when it's molten. So you've broken, when it's molten, this lattice collapses and the ions are free to move around. Go back to our the kinetic theory of matter. When we dissolve in water, the ions are again free to move to conduct electricity. So a solution that conducts electricity is called an electrolyte. Here's our sodium chloride again, and when we dissolve it, we've got these ions. In this case, we're not showing the water molecules, they're just everywhere, and they're assisting this happening, but they're not actually getting in the way or anything. So here's salt, here's water, distilled water, doesn't conduct electricity because there's no free charges. Here's salt, doesn't conduct electricity because all the charges are locked in a lattice. Put the two together and you get water molecules and ions. The negative ions move one way, the positive ions move another way. We conduct electricity. Pretty cool. They are brittle because when you apply a force to this lattice, it distorts it, and positive ions get too close to positive ions and negative ions get too close to negative ions, and they repel. So here's our lattice. We apply a force to it. The negative ion gets next to the negative ion, positive next to positive, and bang! So you should now be able to do all these questions here, and the next video is actually going to be something we've already done in class, but I'm still going to make it and put it up so you can use it for revision. But that's pretty much it for ionic bonding.